Presentation will be about effective nuclear charge, which I've mentioned before, but this is solely going to focus on that topic. All right, so we'll define the concept of effective nuclear charge. We're learning Slater's rules for determining the shielding, and we'll calculate effective nuclear charge using Slater's rules for a variety of electrons. Effective nuclear charge is the pull on a specific electron exerted by the nucleus. It has a relatively simple equation. Z effective is equal to Z minus shielding, where Z is the atomic number, but what is shielding? There are two factors here. First, electrons repel other electrons, which decreases the effect of the nucleus on the electron. Second, core electrons partially shield the outer electrons from the nucleus. Here's an analogy that works for me. You're going to a show. If money is not a factor, would you prefer tickets close to the stage or in the furthest seats from the stage? Chances are you want to be closer to the stage. When you are closer to the stage, you see the show better and are more engaged in the performance. When you're further back, your view of the stage is blocked by other people's heads or their bodies. If you're blocked, you can't see what's going on, you're more easily distracted from the show. So the same thing happens with electrons being attracted to the nucleus. For valence electrons, there are always core electrons closer to the nucleus, and therefore blocking it out. The shielding effect is called nuclear deshielding or electron shielding, depending on which book you try. Of course, the electrons in question are constantly moving, so the shielding effect is actually based on the probability of an electron being in between the valence electron and the nucleus, because it's always a probability factor when you're talking about atomic orbitals. But the show analogy still works because that blocking thing, really easy to visualize that way. We've all been to a show. So let's look at an example. Lithium. The effective nuclear charge is calculated here for each subshell. Electrons in the same orbital have the same Z effective, which makes sense. What it actually turns out to be is if they're in the same group, they have the same Z effective. But I digress. The 1s electrons are shielded by their repulsion for each other. Therefore, Z effective is not 3. It's 2.69. The 2s electron is shielded by the repulsion of other electrons and by the core electrons being generally closer to the nucleus. You can group those two factors into one thing effectively as far as numbers are concerned, which is what we're going to do next when we use Slater's rules in order to calculate these things. So a common method for determining Z effective is using Slater's rules. Slater modified the Z effective equation to include the shielding constant, which is given by sigma, and set up a bunch of rules to describe how to calculate the shielding constant. So first thing you do is group electrons. You write out the electron configuration, and then you rewrite the orbitals of an atom from low n to high n. So in other words, do it by principal quantum number instead of energy level. Then group s and p orbitals by n, and then group d and f orbitals together by n. So for example, we'll have 1s group all by itself. Then we'll have 2s and 2p together. We'll have 3s and 3p together. 3d will be a group. 4s and 4p will be a group, etc. You can keep going. So once you've got everything in groups, you follow the rules for the shielding constant determination. The number of electrons in a group times 0.35 is equal to the repulsion part of the shielding. So you go by the group. Rule number 2, D or F subshells. Electrons in groups of lower energy contribute 1 times the electron, which is equal to the core shielding. So if you're in a D or F orbital, everything that comes before that contributes a full 1 to the shielding. S and P subshells. Electrons in groups next lowest shell contribute 0.85 times the number of electrons, and if it's n minus 2 away or more, It's 1 times each electron. So that total is equal to the core electron shielding. Now this may seem a little bit confusing, but you have to remember that your s and p orbitals are probably closer, those electrons are closer to the nucleus than the d or f, and that's just based off of shape itself. So that's why you have this different calculation depending on whether you're 1 away or 2 away or more for the subshells. All right, and finally, 1s electron, it's 0.3 no matter what the element, which is nice and easy. So let's try this thing. We're going to write electron configurations for the following elements and then group the subshells. So we're going to follow our little guidelines here on the right. So please do that for phosphorus, barium, and germanium. And then the next slide will go through how to do the things. So our first example here, I've written the electron configurations out for each one. It's pretty straightforward for phosphorus because we haven't reached the D or F block yet. Everything is in order of principal quantum number. So then we just have to group it based on our rules. So here we go. We have 1s by itself, we have the 2s and 2p together, we have the 3s and 3p together. Done. Not bad. Now we have the barium electron configuration. Okay, so here we start to get to d orbitals, and as a result, we have this interesting pattern that we've formed where we go 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, 5p6, 6s2. And we reorder that by principal quantum number, and then we do our groupings. Now, when we do that, everything's full, so it's not totally crazy, but it was a bit difficult to do. I like to check things off as I go when I have lots of stuff in order to make sure that I've accounted for everything. All right, and so the next one we have uranium. And when we get to uranium, we have opened up the f orbitals. In this case, we actually have all of the 4f filled, and we have some of the 5f filled. So we have our full order there. We reorder it, and then we group. And the thing which throws me off to no end is the fact that we have 5f4 in there, but it's a result of our electron filling by energy level. Remember that the electron filling by energy level does not follow the principal quantum number. So always write out your orbital filling by energy level first, because you go off Bell principle low to high, and then reorder it in order to do these calculations. So let's try the calculations using Slater's rules to determine sigma, and then we'll calculate Z effective. So I've given you the rules for determining sigma, and then the equation for Z effective. Give that a try. So the first one here is super easy. It's a 1s electron. Only rule 4 applies. Our sigma is 0.3. So 15 electrons total minus 0.3 gives us 14.7. All right, now we're going to try the more complicated 3s orbital. And we're going to do rule 3 first. So if we go to n minus 1, so 3 minus 1 is 2, and we have 8 of those electrons, so 0.5 times 8 plus 1 times 2 for the s orbitals gives us 8.8. Okay, now we go on to rule 1. We have 2 in the s orbital and 3 in the p orbital here, so in that group we have a total of 5. 5 times 0.35 gives us 1.75. So our total sigma is 8 plus 1.75, which is 10.55. When we do 15 minus 10.55, we get 4.45. So our Z effective for valence electron is much, much less than it would be for our core electrons. Let's try the same thing for the 3p. Now 3s and the 3p are in the same group. So we expect to see that they have similar or the same Z effective. So we go to rule 1 first, and the same thing applies. So we have 6 plus 2, 8 electrons in the 2, plus 2 electrons from the s for a total of 8 electrons that are going to be, we have 2 plus 6 equals 8 electrons in the 2 orbital, so 0.5 times 8 plus 1 times 2 in the 1s orbital, which gives us a total of 8.8. So that's our contribution from core electrons. And then we go back and we do the concentration, or the contribution from repulsion. And again, we have 5 in that group, that 3s, 3p group. So we have 5 times 0.35 is 1.75. And when we add those two numbers together, we still get 10.55. It still has the same number of protons, right? So 15 minus 10.55 is still 4.45. This may be a slightly surprising result because we know that the p electrons are a little bit further out than the s electrons, but it's not a big enough effect to matter according to Slater's rules. Now this is completely made up. It's just, it's not from first principles. It's based on empirical evidence. Will we find a first principles relationship here? Eventually, but we're not there yet. So we use Slater's rule to give us a rule of thumb. To summarize, effective nuclear charge is the pull on a specific electron exerted by the nucleus, and in general, Z effective is equal to Z minus the shielding. Slater's rule gives us a way to calculate Z effective using like an empirical shielding constant, and there's rules to how we determine that shielding constant. So we first write our electron configuration. We rewrite the orbitals of an atom from low to high n. We group our s and p orbitals by n. We group our d and f orbitals together by n. And then we have our Z effective is equal to Z minus our shielding. And our shielding is the sum of whatever we get from rules 1 through 4.